The sun affects us directly, of course, when it sends down its heat. But we now know the sun also affects us indirectly through clouds. Clouds have a powerful cooling effect, but how are they formed? In the early 20th century, scientists discovered that the Earth was constantly being bombarded by subatomic particles. These particles, which they called cosmic rays, originated, it was believed, from exploding supernovae far beyond our solar system. When the particles coming down meet water vapor rising up from the sea, they form water droplets and make clouds. But when the sun is more active and the solar wind is strong, fewer particles get through and fewer clouds are formed. Just how powerful this effect was became clear only recently, when an astrophysicist, Professor Nir Shaviv, decided to compare his own record of cloud-forming cosmic rays with the temperature record created by a geologist, Professor Jan Weitzer, going back 600 million years. What they found was that when cosmic rays went up, the temperature went down. When cosmic rays went down, the temperature went up. Clouds and the Earth's climate were very closely linked. To see how close, you just flip the lines.
We just compared the graphs, just put them one upon the other, and it was just amazing. Jan Weitzer looked at me and says, you know, we have very explosive data here.
I've never seen such vastly different records coming together so beautifully to show really what was happening over that long period of time.
The climate was controlled by the clouds. The clouds were controlled by cosmic rays. And the cosmic rays were controlled by the sun. It all came down to the sun.
So here's the idea. We have our solar system continually being bombarded by cosmic rays. Cosmic rays enhance cloud production on the Earth. The more clouds that you have results in less solar energy getting through to the Earth's surface and an overall cooling. Counteracting all that is the solar sunspot cycle. During the peak of a sunspot cycle, we end up with more solar energy, more solar wind, which deflects more cosmic rays. More cosmic rays deflected, we end up with fewer clouds. During a trough of a sunspot cycle, we end up with a lesser amount of solar wind. More cosmic rays get through, resulting in more cloud formation and overall cooler conditions, resulting in this graph that we see right here. So this is a smoking gun to explain what's happening.
Scientists have discovered intriguing evidence from cores drilled in the perpetual ice packs of Greenland and Antarctica. Preserved in the ice is a record of climate dating back 115,000 years. Sulfur deposits in the ice cores indicate that during the Little Ice Age, there was an average of 5 major volcanic eruptions each century. Each of the eruptions had the explosive power of Krakatoa in 1883. Today, such powerful eruptions occur only rarely.
A volcanic eruption puts out particles and puts out gases into the atmosphere. The main gases they put out are water vapor and carbon dioxide, which mix with the atmosphere, but it's the sulfur gases that cause climate to change. If the eruption is strong enough, it will have a plume that goes all the way up into the stratosphere. And these react with water vapor to form a cloud of sulfuric acid droplets, a thin, hazy cloud that's in the stratosphere. It can stay there for several years. And this cloud reflects sunlight back to space and cools the Earth's surface. Less sunlight gets to the surface.
While scientists remain uncertain which natural forces triggered the Little Ice Age, they believe they know what caused the coldest 7 decades within the Little Ice Age's 500-year span. Between 1645 and 1715, near the midpoint of the Little Ice Age, winter temperatures in the northern hemisphere dipped by an additional 3 degrees Fahrenheit. Climatologists trace the cause to the sun, which they believe was weakened by a phenomenon known today as the Maunder minimum.
The minimum there refers to a minimum in the number of sunspots on the face of the sun. And when there are less sunspots on the face of the sun is sending out less radiation, and the Earth is getting less radiation. So if we're getting less radiation, that can cause a global cooling.
Okay, here's Bruegel's Hunters in the Snow. So a picture from Northern Europe. And so this is sorts of conditions that you do not see there at the present time, as existed during the Maunder minimum when there was hardly any sunspot activity and lots of cosmic rays getting in, forming lots of clouds. And it's interesting, if you look at practically any painting that's taken from that, or that was done during that interval, they always tend to have this sort of a hazy, cloudy sort of look to them, which reflects the sort of enhanced clouds conditions that existed, which resulted in the overall cooler type conditions.
More and more scientists are beginning to revise their positions on global climate science. As more data becomes available, it's becoming clear that human intervention is not the only factor leading to climate change, and many scientists are no longer willing to stake their professional reputations on incomplete and unsound data models. But the tide of global warming alarmism is rising. The introduction of the carbon credit system, which is being adopted by government policymakers around the globe, may end up pushing those most at risk for poverty today over the economic cliff. If human beings are the cause for the global climate shift, and if the new scientific orthodoxy of global warming becomes more militant, what is going to happen to the less fortunate among the world populations? Will the reactions to the CO2 emissions problem be inevitably that some of us, or most of us, need to cease to exist so that the most promising of our species can continue to survive on this planet?